welcome back to the Explainer. All right, grab your lab coats because today we are unlocking some of the most fascinating secrets hidden right inside our own blood. We are stepping into the incredible world of clinical hematology to talk about a really special type of cell, one that tells us exactly what is happening deep inside our bones. So let's just dive right in. Every single day, your bone marrow is literally working like a massive, highly efficient factory, releasing brand new, immature red blood cells right into your bloodstream. Today, I want you to think of yourself as a clinical detective. Your mission? To investigate this bone marrow factory and figure out if it's actually working the way it's supposed to. And the absolute best clue we have for this is a tiny cell called the reticulocyte. Here's our roadmap for today. We'll start by meeting the reticulocyte, then we'll check out the bone marrow factory, spot our suspects in the lab, run through normal ranges, break down our ultimate tool, the RPI, and finish up with a super handy retic cheat code.
All right, part 1. Let's officially meet the reticulocyte.
So what are we actually looking at? Well, at its core, a reticulocyte is basically a teenager, an immature red blood cell. You see, as a red blood cell grows up inside the bone marrow, it actually kicks out its nucleus before graduating into the bloodstream. But it holds onto a little something, small amounts of residual ribosomal RNA. And this leftover RNA forms a sort of messy mesh inside the cell. That's actually where the name comes from. Reticulocyte literally translates to network-like cell. Now, the manufacturing process to get there is this perfectly orchestrated 5-stage sequence. It kicks off with a hemopoietic stem cell, transforms into an erythroblast, moves on to a normoblast, and then boom, our star player, the reticulocyte. Once this young cell hits the bloodstream, it's on a strict timer. It only spends about 1 to 2 days floating around before that RNA network totally dissolves, leaving us with a fully mature red blood cell. Moving on to part 2, the bone marrow factory. So how does the marrow actually know when it's time to ramp up production? Well, it's classic supply and demand. When your body is desperate for more oxygen-carrying capacity, your kidneys step into the manager role. They release a crucial hormone called erythropoietin, or EPO. Think of EPO as an urgent, top-priority work order. It travels straight down to the bone marrow and says, hey, we need more fresh graduates right now. And this is absolutely crucial. Counting these immature cells acts as a direct real-time performance review for your bone marrow. If you've got a high reticulocyte count, bingo, the factory is responding perfectly to that EPO work order. It's working overtime. But if your patient desperately needs red blood cells and that count is low, well, that means the factory is failing. The marrow just isn't getting the job done. Which brings us to part 3, spotting the suspects in the lab. Okay, here's where it gets a little tricky. The standard tools most labs use? Totally useless for this. If you just slap an ordinary Romanowski stain on a blood smear, those young reticulocytes are going to look exactly like the mature red blood cells. They just blend right into the crowd. To actually spot our suspects and get to the truth, we need some specialized gear. Enter the supervital stain. We're talking highly specific chemical dyes here, stuff like new methylene blue or brilliant cresol blue. When you apply these dyes, they totally bypass the mature cells and bind directly to that leftover RNA hiding inside our young reticulocytes. And just like that, the invisible RNA pops out under the microscope as this brilliant dark blue meshwork. Suspect officially confirmed, and now we can actually count them. All right, part 4, normal ranges and clues. So when we run a count, we're basically calculating the percentage of these immature cells against the total red blood cell population. For a healthy adult, you're looking at a normal range of about 0.5 to 2.5%. Quick side note though, newborns are naturally going to run a bit higher than this. Their tiny bodies are growing at warp speed, so they demand a much faster, accelerated production line. Now, let's put this into clinical practice. When you see an increased count, that's reticulocytosis, it tells us we have an active factory compensating for something. Maybe acute blood loss, hemolytic anemia, or maybe they're just bouncing back from iron or B12 deficiency after getting some therapy. On the flip side, a decreased count, reticulocytopenia, is a massive red flag for a failing factory. We're talking aplastic anemia, general bone marrow failure, untreated nutrient deficiencies, or even chronic kidney disease, where those kidneys are completely failing to send out the EPO work orders in the first place. Moving right along to part 5, the ultimate tool, the RPI. Okay, we need to talk about why raw percentages can sometimes straight up lie to us. If a patient has severe anemia, their total pool of red blood cells drops off a cliff. So if you look at a simple reticulocyte count and it says 4%, you might think, wow, great response. But hang on, 4% of a tiny number is still a really tiny number. It's a big slice, sure, but of a microscopic pie. The actual bone marrow response might still be woefully inadequate for what the patient actually needs to survive. To fix this illusion, hematologists use the Reticulocyte Production Index, or RPI. The RPI mathematically corrects that raw count by factoring in the sheer severity of the patient's anemia. And the math doesn't lie. If the RPI is greater than 2, the marrow is doing its job, mounting an adequate response, so the anemia is likely a destruction or bleeding issue. But if the RPI comes back less than 2, there's no way around it. You've got an inadequate response. It confirms we are dealing with a serious factory production problem.
Finally, part 6, the RET cheat code.
Let's lock all this in with a memorization framework you absolutely need for exams and hitting the floors. Just think RETIC. R is for response evaluation to identify cell production. R also reminds us of that residual RNA. E stands for erythropoietin stimulated. T is for transitional RBC, because hey, it's just a phase. I tells us it indicates marrow activity, and C reminds us that the count helps classify anemia. Boom! Cheat code unlocked. Seriously, if you take nothing else away from this whole explainer, please let it be this. When you see a patient with anemia, your literal first instinct, the very first question popping into your head should always be, is the bone marrow responding? And the single fastest, most direct way to get that answer is by checking those reticulocytes.
So here's my final challenge for you. The next time you're staring down a complex blood panel, what will those fresh graduates reveal to you about the bone marrow factory? Is the line working overtime, or has production completely ground to a halt? The clues are literally swimming right there in the bloodstream, just waiting for you to find them. Keep investigating, keep asking those big questions, and I'll catch you in the next explainer.